Welcome to the 14th lecture for Physics 4B. We are wrapping up and reviewing electrostatics in this lecture. We start with the dipole lecture. This introduces a picture and a way of looking at charges and fields that'll be useful when we get into magnetism. And this will also be an excellent setup to review the concepts and techniques we learned in electrostatics. After reviewing electrostatics in a table form, we will solve a couple exam type questions titled Extended Charge Field Calculation and Conducting Plate. This is it for electrostatics. And as we continue on to circuits and magnetism, the concepts we have introduced as well as the calculational techniques will continue to be useful. I'm just going to call it dipole lecture because that's what it should be. And biggest reason I want to do this dipole lecture is that for now, this is an electric dipole lecture, but later on, a lot of this can be repurposed for magnetic dipole lecture. A lot of the things that we'll be bringing in the context of electric dipole will still apply for a magnetic dipole. So that's really the reason it's important. So as a reminder of something that you have seen before, it's an arrangement of a positive charge near a negative charge. They are of the same magnitude. And the other parameter that's important in determining characteristics of dipole is the distance between the two charges. So if you have two charges separated by distance d, then we can define something that's called electric dipole moment. And electric dipole moment, if I'm remembering, this is where I want to use the letter P. I don't know if that's the common letter. So electric dipole moment can be defined as the charge times the distance of a separation between the two charges. And there's a way to define this as a vector. But for the purpose of today, I won't get into that formal description. I'll just, and I probably won't even use electric dipole moment. So let me scratch that. And just to talk about electric dipole as something that you have seen before. So when you have arrangement of charges like this, you know what the electric fields look like. That's the context where you have seen electric dipole before. As we are introducing the electric field lines, you've seen this as a way to illustrate how electric field lines come out of the positive charge and go into the negative charge or go out into infinity. So you have seen that. Now, one of the importance of electric dipole is it's how common it is. Because a dipole is a very common way we model electrical interactions, especially when something doesn't carry a net charge. It's such a common electrical object, and understanding it well it's useful for applying what you learn in this class for what you might be asked to do in other classes, chemistry, biology, whatever. So I wanted to describe some of the dipole interaction and use the remainder of maybe 10 minutes or so to do something mathematical with the dipole potential and the electric field due to a dipole. So let me talk about that dipole interaction. I think when I talk about dipole, I really want you to think about an object that's just an object with a separation between the charges, positive and minus, with some distance between them. And I guess it's simplest if we imagine this distance as being constant. And the easiest way to get an interaction between a dipole and anything else is to simply talk about the interaction between an electric field and a dipole. The simplest electric field I can imagine is a uniform constant electric field. So let me draw a representation of that. I have some region of space with a uniform electric field. For the moment, I don't worry about how that electric field was generated. And this might be truly uniform, or I might be approximating something as being uniform by considering small enough a region where electric field doesn't change much. So if you imagine having this dipole in this region of uniform field, there are some things you can talk about. I guess the easiest place to start from is what is the net force? Because that's usually the thing that we ask about whenever we are dealing with mechanics. And this is a mechanical thing. I have a mechanical object. So the natural question to ask is, what is the net force? And when you consider that, I think you will quickly see that net force becomes not as interesting with the dipole. So imagine I have charge of plus Q here, and I have charge of minus Q here. And okay, let's draw a free body diagram. For this charge of plus Q, I have a force of QE pointing in the same direction as the electric field. On this charge of minus Q, I have the force of magnitude QE pointing in the opposite direction as the electric field. And you can see that as an object, as a whole, the net force here will add up to 0. And, and that's generally true. Whenever the electric field is uniform, the net force on a dipole will be 0. And this might kind of disagree, maybe even violently disagree with your intuition, because in the very example I showed leading to this, didn't I show a force being applied on this aluminum tab, right? I mean, isn't this aluminum tab moving because of a net force? So what I mean net force is 0 on a dipole. Any net force on a dipole has to involve a non-uniform electric field. The derivative of the electric field has to be non-zero, so that there is a difference between the amount of force on one side of the dipole and the other side. So, so you will see that handled eventually in some upper division class. For the purpose of this class, I'll say with a uniform field, net force on a dipole is 0. For a uniform field. And as far as the theoretical calculations go, we will almost never do calculation involving dipole and a non-uniform field. So with the net force being 0, there are still some interesting things that can happen to a dipole. When you look at this arrangement of the charge and the field, what you are still seeing is that so I hope when you see a free body diagram like this, your intuition doesn't say that nothing interesting happens here, because even though the net force might be 0, I hope the forces you see makes you think, oh, it's going to rotate. That's so what we can talk about, even with the net 0 force, is what the net torque would be. So there is going to be a net torque on the dipole. And for this, let me just give you the formula, and I will leave that up to you to verify that this formula is true. The net torque on a dipole, this is how I have it memorized, is the electric dipole moment cross product with the electric field. And these are all vector quantities, and these are all vector products. And for the purpose of complete description, this dipole moment as a vector quantity is defined to point in the direction of this displacement vector d. And the electric dipole moment is defined as the charge times d. So let me just leave that there. I mean, this is the piece that I want to come back to when we start talking about the magnetic dipole. Some of these formulas will just fit right into magnetic dipole interaction descriptions. But for the purpose of what we are talking about right now, electrostatics, we won't really be using this torque formula. So I'll just state it, leave it there. And well, second to last thing to talk about with the dipole interaction is when you have a torque on an object, this torque can do work. And when torque does work, that'll result in change of energy. Work done by torque on a dipole will result in energy being stored on that dipole and the field arrangement. So you can kind of see it here. This is sort of what I imagine. When I stare at this setup, I can visualize that if something was holding this dipole, and you suddenly let go, it's just going to start rotating on its own because of the electric field. And what that indicates to me is that this dipole was in some setup that was at a higher potential energy, and it's rotating into a position of lower potential energy. And you can think about playing with this setup and kind of rotating it around, seeing what position would have highest potential energy, what position would have lowest potential energy. And when you're done playing with it, the position of highest potential energy you will find is this one with a positive charge here, negative charge here. So the displacement vector and the dipole moment pointing anti-parallel to the electric field, because it's from this position where it'll rotate around. And the position of lowest potential energy is this flipped around, where you have negative charge here and positive charge here. And the dipole, the displacement and the dipole moment is pointing parallel to the electric field. So you can imagine once you have an electric dipole that's oriented this way, then further electric force will simply keep it maintained at this position. So that's the position of lowest potential energy. And I'll leave this also for you to work out the detail. There's a formula for the potential energy of a dipole interacting with an electric field. And that formula for the electric dipole is minus P dot E, where P is the electric dipole moment defined here, and is the electric field. And you can see it here where the dipole moment is pointing in the same direction as electric field. So this dot product is most positive it can be. The potential energy is the most lowest negative it can be. And when it's turned around and anti-parallel, its potential energy is the highest it can be. And this formula is defined so that at the position where it's perpendicular, it's defined to be zero. So, you know, with the potential energies, it's always the difference that's dynamically meaningful. And here the zero is set so where the dipole is at the 90-degree angle, where the torque on it is greatest. Not that that matters for the definition. So let me leave this for you to consider, and just to know, with that I did need to introduce these for reference again when we get to magnetic dipoles, because these are some useful things to talk about when we have physical objects that can be described as magnetic dipoles. And the thing about magnetism is it's sometimes difficult, sometimes not very intuitive, and it's good to have other analogies to fall back to, something more familiar that you can use to compare, to see if what you're thinking about with magnetism makes sense in the more familiar context. And let's see. I said this would be the second to last thing about interaction I would talk about. And yeah, I probably should do, at least to mention this, which is the term and the idea of self energy. This isn't something I think that we draw a lot of attention to deliberately in lower division. But I think this is still an appropriate place to do that, because by self energy we don't really mean anything mysterious. You have in fact seen it when we talk about energy stored in capacitor. The formula for that is 1/2 QV, and this is an example of self energy. By self energy, what all we mean is energy involved in energy that is involved in, stored in, distribution of charge itself. So what I want to distinguish here is that this particular energy here, it describes the interaction between the dipole and something external, whatever the external thing it is that I must have used to set up this electric field. That's what that energy refers to. When I talk about self-energy, it's the energy of the object that's there because of the object that's there. So in the case of dipole, if you have a positive charge in the vicinity of negative charge, there is potential energy associated with this arrangement alone. I mean, I can just quickly go through that. This negative charge being here, it generates a potential. So at the distance of d, the potential due to that negative charge will be Coulomb constant times minus q over d. So this positive charge that's here, it's at that electric potential. So there's a potential energy of interaction for this positive charge, and then interaction energy will be the charge, amount of charge plus q times the potential, or minus Coulomb constant times q squared over d. So this is negative, which means it's a bound state. The positive charge and the negative charge, they attract each other, so they are bound to each other, and so there's that self energy. That's the self energy of a dipole. And I guess I thought this would be worth pointing out, because I think as we are talking about electricity, it is a fundamental law of nature. Almost everything in life has some electrical thing that's making it up, protons, electrons, not neutrons. And sometimes there's this kind of turtles all the way down feeling, where it's in the old mythologies about the model of the world. I guess one of the Asian mythologies, world is like something built on the top of a turtle, and, there's some amusing anecdote about a cosmologist who was giving a talk, and a woman claiming that all that's nonsense, and the woman says the world is, something on a turtle, and the cosmologist asks, okay, then what's underneath the turtle? And she says there's a bigger turtle, and it's turtles all the way down. Sometimes it can get that way with the self energy. I don't mean this only as a joke, because without getting too deep into this, I want to just invite you to consider self energy of a point charge. And I think I can do one as a kind of a quick example, not of a point charge, but of a spherical shell, of a uniform spherical shell of charge. So let's say I have a spherical shell of charge, total charge of plus q. There's energy. there's energy involved in bringing this amount of charge together in that spherical arrangement. I happen to know that voltage along the shell here, V is equal to Coulomb constant times Q over the radius of the shell. So you might think the potential energy of the charges on the shell here is that potential energy is the amount of charge times the voltage, or Ke times Q squared over R. It turns out there's a factor of a half. For the same reason as there was a factor of a half for the capacitor. You can get this half in different ways. You can get it through either integration, imagine building up that charge gradually, or you can get that by deliberate double counting and then divide out the two, so because you double counted. So this is the expression for the self-energy. This time it's a positive, so it takes energy to bring those charges together, put them in a confined space. Otherwise, they would just repel each other. And when I talk about point charge, a point charge is something that's at a singular space. It doesn't have a finite radius r. To the greatest extent we can determine, it's at a singular space. Electron is an example of real life point charge, as in we don't know a structure of an electron that there's no such thing as a size of an electron. And that's where you run into a bit of a difficulty because if you took this formula as a given and you let R go to 0 because it's a point charge, your potential energy goes to infinity. And so in this lower division electrostatics class or electromagnetism class, we ignore all that. So we are not going to talk about self-energy of a point charge beyond this one amusing mention of it. And we are probably not even really going to talk about self-energy of dipole all that much. We are going to talk about energy of a dipole interacting with external fields. And because there are some pointed exceptions, as in self-energy of a capacitor, I want to highlight this so that it's not confusing when we are talking about energy of a dipole interacting with an external field, there's no factor of 1/2, like that's not here. But there's whenever we are talking about energy of a capacitor, or later on when we talk about energy stored in an inductor, there's going to be another factor of 1/2 again. So because that can sometimes seem very arbitrary, I want you to highlight that so that you know where that factor of 1/2 comes from. So this is the description of a dipole interaction with an external field. Let me move on to the final piece of this dipole lecture. So this is going to be application of something you learned last week and we were wrapping up this week, which is application involving electric potential and fields. So let me title it that. So let me set up the situation. So I'm going to have a coordinate axis. Let me set up my dipole in a way that's more manageable, symmetrically around the origin. So let me have a positive Q here, minus Q here, and they are going to be separated by distance d. So you know what coordinates they are at. This is at 0, d/2, and so on. I think this is the exact same setup your textbook uses. So I guess the thing to do right now is to figure out the electric potential due to this dipole arrangement. So I want to write down electric potential of a dipole as a function of x and y. And I could also have a g coordinate here. The way I set this up here, the spatial axis here is y. because that's the axis that the displacement is along. If you want to introduce a z-axis, you can kind of do it alongside the x. Once we have a form, it'll be clearer how it can be introduced. So let me just pick a representative point for which to describe the electric potential. Now, there is a very distinct advantage in dealing with the potential. You can see it even here, which is that I think you have never seen me try to figure out electric field of a dipole at an arbitrary point out in space. I might have done that in one of the lectures, let's say along the axis here, like I can pick a point here, and I can figure out electric field due to this. I can figure out, okay, positive charge, electric field points that way, negative charge, electric field points that way. So this is going to be the net electric field. Let's figure out the components and do all that. I can do that for here, and I can do that along the axis here. But any arbitrary point, I mean, I can come up with some expression, but that expression is going to be horribly complicated. So it's really not worth doing it, so I've never done it. With the potential, it's not going to be all that complicated. And the biggest reason for that is potential is a scalar. So you saw the very first thing I did when I was trying to figure out the electric field. I looked at the components, I drew the arrows. With the potential, I don't have to do any of that. All I have to do is to figure out, okay, what is the potential due to a positive charge? What is the potential due to minus charge? And once I have those, simply add them together. That's my combined electric potential, and then I'm done. I don't have to figure out the components. I don't have to do any of that. So let me do that. One thing I do need to figure out is the distance. So there's this distance r plus, and there's this distance r minus. And I do need to figure that out because this is the formula I'm going to be relying on. That electric potential due to a point charge is the Coulomb constant times the amount of charge divided by the distance. And this distance is the distance from the charge to the point where I'm calculating the potential at. So let me figure out those two quantities. R plus, let's see, I think it's easiest if I draw this triangle. So this side of the triangle is simply going to be x, and this side of the triangle is going to be y minus d half. And here's a kind of an amazing thing. This expression will work for all the points y in all four quadrants because I'm going to be squaring it. So it's really the magnitude that matters. So even if y is, I don't know, between 0 and d, it's still going to work. Even if y is 0, it'll work. Even if y is negative, it'll work, because when you take the negative quantity and subtract d over 2, the magnitude is going to increase. So I just want to highlight that this expression is something that works not just for the point I illustrated here, but it works generally. So given these two legs of the right triangle, the hypotenuse is given by the Pythagorean theorem, square root of the x squared plus y minus d half squared. The r minus, that's given similarly. Let me consider this triangle here. So it's going to be, the x component will be the same. The y component this time will be y plus d over 2. This will be y plus d over 2. And as before, this expression will work for all the different points in the space. So x squared plus y plus d over 2 squared. So all right, I have the two distances. So my potential, it will be this. So the potential of the dipole arrangement here will be the potential due to the positive charge plus the potential due to minus charge, which will be K times Q over R plus square root of x squared plus y minus e half squared plus K sub e times minus Q over square root of x squared plus y plus d half squared. Um, so you can simplify this a little bit, but I guess, well, let me first do the simplification that I can, which is I can factor out k times q. And yeah, so let me do that first, k q. And then what you have in here is 1 over this quantity minus 1 over this quantity, x squared plus y plus d over 2 squared. And I guess as long as you're dealing with a finite d, as in finite charge separation, there isn't much more you can do. You're kind of stuck there. And so this is where it's useful to consider this limiting case, where d is much smaller than, well, much smaller than r plus or r minus. And you can actually consider this in two different ways. One is to say that you are considering points very far away. That's one. The other way, which is more interesting from practical application purposes, is to consider the case where it's d approaching 0 in such a way with a corresponding change in charges so that qd is constant. That's another way you can bring about the same limiting case. In the end, the limit is the same, that d is much less than these distances. And that implies one thing. It implies that d is much less than x or y in terms of absolute value. So when you consider the limit, considering the limit allows you to simplify this setup quite a bit and kind of highlight why this quantity is important. So I'm going to pull a, I don't know, rabbit out of a hat. So this is what I want to consider. As I look at this, I see how similar these two expressions are. I mean, you know, they are not similar enough that I can simplify them more. This square root is just maddening me in the way. Really, these two expressions are different, only in that this is minus and this is plus. And in fact, I can even write it down this way. Let me define a function f of y as 1 over square root of x squared plus y squared. So that's a function I'm defining. And I can express what is here as f of y minus d over 2 and define, so define what's on in the second term as f of y plus d over 2. So with that description, what is the difference here that looks like is f of y minus d over 2 minus f of y plus d over 2. Now, this is the trick I want to use, which is I want to rewrite this expression in this way. Let me divide it by d and then multiply by d. I'm just multiplying a number by 1. I'm allowed to do that. You can't stop me. And this limiting case that I was talking about earlier, let me apply that limit to what I see here right now. Let me say limit as d goes to 0. And I guess I'll apply that limit to that d over there, but for now, let me limit my attention to this portion here. I hope you are getting my hint at what I'm getting at here. This is conspicuously written in a way so that it looks like a definition of derivative. I do need to fix a few things. I think I need to move this one here, so there might be a minus sign in front so that this can be plus and this can be minus. The thing here is that it's a difference between a function divided by the parameter that's causing that difference. Take the limit where that parameter goes to 0. That's the definition of a derivative. So let me do that. I'm going to replace what's in here with this. I'm going to replace that with the minus of the derivative of the function with respect to y. I'm going to leave x alone, times d. That's this d here. So now, in general, that's not precisely correct, but this is the magic of calculus. This is the magic of the limiting procedure, that in the limit where d goes to 0, that gives you the exact result. So let me take the derivative. All right, let me rewrite it this way first. Y squared raised to the power of minus 1/2, and it's this thing that I'm taking derivative of. So now I can use power rule, bring down a factor of minus 1/2. Let me finish using the power rule. Squared plus y squared to the power of minus 3/2, and using the chain rule, I'm applying the derivative to the inside, so it should be times 2y. Okay, so the half cancels out with the 2. So I end up with equals minus y divided by x squared plus y squared raised to the power of 3/2. All looking good, I think. So let me plug this expression into that space there, and I will write out the cleaned up version here. So the electric potential of a dipole is equal to Keq times, and I notice I have a minus sign here, and I'll have minus sign there. That'll cancel each other out. So I'm just going to write down the positive quantity. I have y here, I have d there, so let me write those. Let me write d first. D times y divided by x squared plus y squared raised to power 3/2. And let me just check the units to make sure that units make sense here. So with the electric potential, you should have a unit of Coulomb constant times charge divided by a single factor of length. So I have here so far 2 factors of length on the numerator, and in the denominator, squared, square rooted, raised to the 3rd power. So 3 factors of length. So I probably didn't make any algebra mistake. And so this is what you see with the electric potential of a dipole. I guess, let's see here. This is where you see the meaningfulness of the electric dipole moment, the charge times the displacement. So we can treat this as a constant, and the rest is a function of position. And in the limit where y goes to infinity, what you see this potential doing is it's proportional to y divided by y squared raised to 3/2, or 1 over y squared. So So with the point charge, the potential went down as 1 over the distance. With the dipole, the potential goes as 1 over distance squared. And that's a general feature you would see in a dipole potential, that it falls off more quickly than a monopole potential does. And it's the same thing for a quadrupole. The potential for that goes down more quickly than a dipole potential would. So that's a electric potential. And let me use this expression, the electric potential of a dipole, to derive expressions for electric fields. That'll give you something you can compare to and see how much easier it was. I guess if you're comparing to, maybe rather than relying on this expression, let me go back to my earlier more exact expression where I didn't take this limit yet. So yeah, let me do that. The comparison with expressions of for electric field that you might have seen elsewhere. So for the purpose of that comparison, I won't take an arbitrary point because frankly, with arbitrary points, we don't have anything to compare to. What I will do is I'll take a point along the x-axis that is easy enough to do the same calculation with electric fields and compare. And I will take a point along the y-axis. That's the same deal. Easy enough to do calculation for the electric field and compare. So I just want to do a quick calculation for electric field along the x-axis. So that would be electric field at some arbitrary points over x and where y equals 0. That's a calculation that I think I can do fairly easily. So this is where you see usefulness of electric potential for more, I guess, theoretical calculations. Because to do this calculation, all we have to do is take the expression for the electric potential as a function of x and y. I really do highly recommend that you hold off on plugging in these values until the very end. Sometimes if you plug it in too early, you zero out a term that you shouldn't have zeroed out. So potential as a function of x and y. You take the derivative with respect to, so it's really the component that you care about. And here I know intuitively enough that at points along the x-axis, the electric fields only point along the x direction. So if I find the x component, I'm done. And I can also do the same calculation with the partial derivative with respect to y, but I'll leave that for you to try. So to find the x component of the electric field, actually, sorry, my intuition was wrong. It's not. With this arrangement, my electric field is not along the x-axis. It is along the y-axis. So yeah, because it's going that way, yeah. So that's gonna be the direction of electric field. So let me find the y component of electric field with a partial derivative with respect to y. And I need a minus sign here. And for your own exercise, you can try taking the partial derivative of the potential with respect to x. And after having done that, when you plug in y equals 0, you will see that that goes to 0, showing that the x component is equal to 0 for these points that we are describing. So let me take the derivative. The main usefulness here is in that the derivative is usually mathematically easier to take. So when I have this and this, I can just take the derivative term by term, and this is easy enough of a derivative to take. So let me first factor out k, q. That's something that's going to be a common coefficient for all of them. So for the first term, I'm taking the derivative of this term here, which is, maybe it's worth rewriting this right now. Let me rewrite it as kq times x squared plus y minus d over 2 squared raised to the power of minus 1/2 minus x squared plus y plus d over 2 raised to power of minus 1/2. So that I can use power rule and then chain rule and then power rule. So it's gonna be minus 1/2 x squared plus y minus d over 2 squared minus 3/2, and then chain rule for this inside here times 2y minus d over 2, and then, well, I can use chain rule again, that'll give me 1. So I'm done there. And then let me do the second term, which will give me minus times another minus, so plus 1/2 x squared plus y plus d over 2 squared minus 3/2 times 2 y plus d over 2. All right. So having worked all that out, I see simplifications. I mean, there are some things that simplify right away. Half cancels 2, half cancels 2. And the other great simplification will really come in when I plug in y equals 0, which is why there was a calculation we could do even just for straightforward calculation of electric field. So when I plug in y equals 0 here, not only does y go away, this minus sign no longer becomes relevant, because when I square it, the minus sign will simply go away. Same thing here, y is 0, and this was already plus. And what that does for me is this term right now is now the same as this term here. It just magically. And y is 0 here. Now this minus isn't, it's meaningful, so I can't get rid of that. So 0. And this y is 0. And this plus, it's meaningful, I can get rid of that. And that's actually an important thing for this calculation here, because it's this minus sign that cancels out this minus sign here. Otherwise, without that minus sign, these two terms would have just canceled each other out. In fact, that's exactly what happens with the x derivative. That's why the x component is 0 here. So with all that, let me write down the simplified version. The KQ, what else is in the numerator? I think I see d over 2. Yeah, so KEQ times d over 2. So you have that product of q times d, which I'm telling you is meaningful as a dipole moment, divided by x squared plus d over 2 squared raised to power of 3/2. Yeah, I didn't forget anything, I hope. I think I got everything. And so that's the answer. And what you see in this expression here is that electric field due to a dipole goes as proportional to 1 over distance cubed. So all the numerator factors are constant. And if you imagine taking x to a value that's much bigger than d over 2, then you have x squared raised to the power of 3/2. So x raised to the power of 3 in the denominator. And this kind of dependence of the electric field on the distance is characteristic for a dipole, goes as 1 over distance cubed. So it falls off much more quickly than a monopole field does. So that's for electric field along the x-axis. Let me do the electric field along the y-axis. After scrolling down a little bit to make room. So this calculation is... So let me call this just the electrostatics review, since that's what's requested and that's what I will attempt to do. So there is a benefit in doing a review that that you don't have when I'm first introducing the topics. One of the benefits in doing review is that we are not forced to introduce topics in the order it has to be introduced. So we couldn't possibly start the week 5 with a discussion of electric field, because in order to introduce electric field, we had to talk about force, and so we had to talk about Coulomb's law in that way. So the benefit in doing review is that I can assume that you have seen all this at least once, the first time. So in the review, I can introduce these formulas and topics and definitions in the way that makes more logical sense without having to worry about the chronological order. This is one of the reasons that physicists make terrible historians, because chronological order isn't really the way we think. So now, as I'm thinking about electrostatics, really the place I would start is the definition of electric field. That electric field is defined by this relationship. That electric force, which is what we are actually able to measure in lab, is given by electric charge multiplied to electric field. This is the defining expression for electric field. And whenever you are confused or not sure about whenever you feel like you are losing grip on electric field, this is the expression that you come back to, because that's the defining expression. And, I think I justified why I'm writing it in such a weird way. I'm claiming I'm defining the electric field, but it's because I don't want to I don't want to imply that electric force is more fundamental than the field. We believe that the field is the fundamental thing, which is why I want to start from the field and get to the force. So with that expression, there are some useful formulas to have memorized. These are the electric fields of different charge distributions. The first is really what we introduced in Coulomb's law, electric field due to a point charge. Electric field, the magnet, do I want to say magnitude? Let me give the vector representation. The electric field due to a point charge is given by Coulomb constant times the charge that's producing the field divided by the distance squared, and the vector points outward from the charge if the charge is positive. So r hat is the radial vector that's going outward. So that's the electric field due to a point charge. And in application of Gauss's law, we have derived these, two more formulas, but technically 3 additional formulas. So there's the electric field due to a sphere outside the sphere that happens to have the same form as the electric field due to a point charge, but I have to specify this distance from the origin is greater than the radius of the sphere. Once you are inside the sphere, then uniformly charged the sphere, then you have to apply Gauss's law to find the form of electric field. I won't write that down in this review table, because that is where you actually should know how to apply Gauss's law yourself. That you should be able to use the symmetry argument to be able to argue for yourself. K, Q, and closed. Well, sorry. Let me rewrite that. I ran out of space there. So Gauss's law. Gauss's law is one of those things that's hard to capture in a review table. I can write down what the Gauss's law is, and really, this is a shorthand for saying you should know how to use this plus symmetry argument. You should know how to use this to derive any formulas in any new situation that you may not have seen before, to the extent that symmetry applies. And in a class like this, I won't give you situations where things are either not symmetric enough that you can't use Gauss's law, or if it's not some kind of arrangement you can build out of other things that you know about, which I'll get to actually in a bit. So through application of Gauss's law, there are three more electric field formulas that I derived. I just wrote down the one for the sphere. There's a second one due to a line of charge. So electric field due to an infinite line of charge is given by 2 times Coulomb constant times the, here it's not going to be a amount of charge, it's going to be charge density because it's infinite line. The actual amount is infinite. So linear charge density lambda divided by distance r, distance from the line, times r hat. And here I'm committing a little bit of notational abuse because I'm using this r to mean the mean two different things. Here, this is a vector, unit vector that's radially going outward from an origin. So it's outward from a single point. Here, this r hat is radially outward from a line. So it's perpendicular to the line. Just, you know, as you're remembering this, remember those differences. And sometimes people do use actually different letter here to remind themselves that like S is a common letter to use here. But in the end, it comes down to you have to remember what direction these things are. And the final formula is the electric field due to a plane of charge. And that's given by, do I remember? Yeah, 2 pi times Ke times the surface charge density and times the normal vector. And this is a interesting formula that doesn't depend on distance. That's a result that we derive out of application of Gauss's law. So that's the summary of electric field formulas that you should know. And the addition to this, which isn't a formula, but it's a principle that you should know, is the superposition principle. Because there may be situations where you recognize that you don't have enough of a symmetry. Maybe it's a charge distribution that's a combination of an infinite line and a plane. Then you don't have the requisite symmetry to apply Gauss's law just directly. But what you can do, maybe you can figure out two distinct parts to which symmetry arguments can be applied independently. And then after that, you can combine them together. So, so that's kind of the short description of how you might be applying superposition principle. I'll end this review with the statement that this is what a lot lets me add some variety to the questions that I could possibly ask about electric field due to different charge distributions. Because without that, it could be, I'm basically limited to what you have already seen. But once I can combine two or more of the things that you have seen, then the combination can get more interesting. So this covers first 2 weeks. What we've been covering, does this cover first 2 weeks or first 3 weeks? Maybe first 3 weeks. What also covered under electrostatics that I should write down here is the idea of a voltage or electric potential. So this portion here basically covers electric field. When we are talking about electrostatics, there are really two important concepts that are highly mathematical. There are things associated with them that you should remember, which is electric field and electric potential. So I've been talking about electric field. So let me talk about electric potential. And there are multiple binding places for electric potential. Two different places. There's you can introduce the idea of electric potential through its association with electric potential energy. And this is the relationship that would relate them together. Oops, I'm writing it opposite, the other way around. So the electric charge times the electric potential gives you the electric potential energy. Um, there's a, and when you look at this relationship and this relationship, I hope that they look familiar because they are constructed that way. Um, the field was basically the version of a force where you could take out the interaction with the test charge. The electric potential is the version of the potential energy where you can take out the interaction with the test charge. Now, with the potential, I do want to say this is not how we define it. This is one of the mathematical relationships that happen to be true. The actual definition of electric potential is done through this relationship. The change of electric potential, let's say going from point A to B, is given by the line integral of the electric field as a function of position along a path, dot product with the path element. And the whole path is some path going from A to B. And there are some properties about conservative forces and fields where this actual integral doesn't depend on the specific path taken, so you can choose a convenient path. So this is the actual defining expression for electric potential. And even though this is not technically the topic this semester, but sorry, I always, and I think I did this in the prior video too, always forget a minus sign. So this is, although this is done in analogy with something we did or supposed to have done in physics 4a, which is how we define potential energy. Potential energy is done through it's defined through the work done by conservative force. The change in potential energy is defined as minus work done by the conservative force, or the line integral of minus the force dot product with the path element going from A to B. So this is in the background, and that's how these three things are related to each other. So with this, there are a bunch of formulas that are also again derived. That's good to know. There's the potential due to a point charge, and it's in this context where I introduced the idea of universal reference, which is so let me write down the formula. Electric potential due to a point charge, or voltage due to a point charge as a function of distance, is equal to the Coulomb constant times the charge divided by R. And here's a nice thing about potential, which is it's a scalar quantity. You know, when I was writing this down, I was wondering, hey, should I just deal with magnitude or vector? Decided to write down vector. With the potential, I don't have to even worry about that because it's just it's scalar. There's no direction to worry about. And when I'm writing down this formula, I do have to specify this formula is true with this reference specified that voltage goes to 0 as R goes to infinity. And you can see it here, you know, if R goes to infinity, if V of R goes to 0. And the reason I have to always specify this either explicitly or implicitly is because it comes from here. It's only ever the change in potential energy that's physically meaningful. So it's also only the change in electric potential that's supposed to be physically meaningful. So I have to specify where I'm measuring my difference from. And I think with the electric potential of a line and a plane, it's hard to write down a formula like this, mainly because these are infinite charge distributions. So if I try to set this reference, it doesn't work. So whatever formula I write down, it depends on where I set the reference. So I want try to capture that in a table. Maybe one last thing before I wrap it up here. Well, two last things, because after I wrap it up, I should at least write down the definition of capacitance. So the one penultimate thing, it's the inverse of this relationship here, because it is implied by the fundamental theorem of calculus, and I think that's the name of the theorem. But to make it explicit, you can actually get electric field from the potential That's really why it's useful to find the potential first sometimes, because once you know the potential as a function, then using that, you can get the electric field. So for example, the x component of electric field at a particular point is the partial derivative of the potential at that particular point, you know, x, y, z, with respect to x. That gives you the x component right away. So you can imagine doing this for y, t, to build up the full electric field. And if you have already taken multivariable calculus, then you might, sorry, I always forget this minus sign. There's a minus sign there. um, if you've taken multivariable calculus, then you might be able to understand this expression, which is that electric field as a vector is the negative of the gradient of the potential. I don't know if you call this field. Well, potential function as a function of all the coordinate variables. So this is the penultimate thing. And the very last thing, which I should cover because it's going to be covered in your timed assessment, which is the capacitance. And they're really the thing that would be captured in a compact review is the definition of capacitance. Capacitance is defined as capacitance C is defined as amount of charge stored in some arrangement, which usually involves two conductors, and you have positive plus Q on one, minus Q on the other. So amount of charge is stored, and there's a voltage difference between those two conductors. So take the amount of charge divided by V, that'll give you capacitance. And the thing that may be a little bit surprising that you should know to expect is that this depends only on geometry, plus dielectric constant, material property. But what it does not depend on is the voltage difference or the amount of charge. It always works out so that, so if you write down V as a function of Q, there will be a linear factor of Q in the denominator that will cancel out with the charge on the numerator. So yeah, this is a like 20-minute review of electrostatics. I, I may have left out some things that I've covered previously, but this would be a second version of the review that, you know, if it's not word for word the exact same thing that's in the other video, then it should cover, there should be at least 80% overlap. Yeah. Okay, so once I start, you know, the 20 minutes of time is really short amount of time, even for me. So, so I will be careful in my use of time, and I think there aren't that many questions in electrostatics where use of computer algebra system will actually save me time. So I'll just do everything, all the required math by hand. I won't use computer algebra system. So with that, I'm gonna start the assessment. Just make sure it's not the one I did before, and then just try to finish it in 20 minutes with some explanation. Okay, yeah, that's not the one I did before, so let me do that. Okay, it says consider 3 different situations given below. For full credit, give full correct answer to at least 2 situations if time allows. Oh wow. Okay. Let me try to do all 3. See if I have enough time to do all 3. So for it to calculate the electric field, okay, give both magnitude and direction. Okay, just the electric field. All right, that's good. So consider dipole arrangement shown below. Yeah, that's just a word description of the arrangement, and it's asking for magnitude of E. Okay, so let me start with a picture of the setup so that I can point out some things that you should consider. So plus Q, and we are looking for electric field along the dotted line. Oh wow. Okay, so I needed to calculate the electric field as a function of y along here. What's useful for me to note is that x is 0 along this line. That helps me simplify some things. So I'll pick a representative point. Let's say a point here. And visualize the electric field due to each of these charges. So from charge plus Q, there should be electric field pointed that way. From charge minus Q along this line, there's an electric field towards minus Q that way. So once you draw these figures, I hope you realize that the y component of electric field will cancel out. So the only component of electric field you have to worry about is the x component that adds up to something like this. Realizing this helps simplify your calculation because you only have to worry about the x component of each of these contributions and not worry about the y component, knowing that they will cancel out. And in fact, the direction of electric field is in the plus x direction. So magnitude of E. Now I have to use Coulomb's law. Coulomb's law tells me the formula for the electric field due to a point charge, which is going to be Coulomb constant times the amount of charge divided by distance. Let me not use d because that's already there. Divided by distance squared. So for the contribution from the positive charge, I know that its magnitude will be Ke plus Q divided by now I have to work out the distance. So this is d over 2. This is where this being representative point with the coordinate y tells me this leg here. That should be y. That allows me to calculate this hypotenuse, which is going to be square root of the squares or sum of the squares of the legs. There. So I'm going to take the hypotenuse, square it, so the square root will go away. So for magnitude, it'll be d over 2 squared plus y squared. And I'll handle the x component in a bit. Let me work out an expression, or actually I was thinking of working out an expression for the magnitude of the electric field contribution from minus Q, but I think from symmetry I can see that this will also be the same magnitude for that contribution. And in fact, if I just work out the x component here, then I can just double it. That'll give me E net. So I can just let this be double of that. So let me, I'm doing wrong kind of undo. So let me just work out the x component of that. So for the x component, I'm basically considering this triangle here. That's the magnitude, and I have these two legs. And for the x component, I'm looking at this leg here. That's what I'm trying to figure out. So I need this angle here, which I'm not given, but I think I have enough sense of geometry to know that this angle is same as this angle here. So this triangle will help me figure out how to get the x component. So, in terms of just the mathematical expression, the x component will be the magnitude times adjacent side, so it should be cosine theta. And so theta is, so I could say, I know the two sides, y and d over 2. So I can say theta is arctangent of y over d over 2. So if you said the x component is e plus times cosine of arctan of y over d over 2, and if you gave an answer based on that, I wouldn't say that's wrong, but there's a calculational technique that'll actually allow you to get a algebraic expression for this, analytical expression for this, that doesn't rely on inverse trig functions. And it's the technique called drawing the triangle, which I've already drawn. So let me finish it completing the triangle with the label for the hypotenuse, which I've worked out before. Square root of d over 2 squared plus y squared. And the amazing thing you have here is that once you have all the sides of the triangle, you have the tool for looking up any trig function you need. So, cosine of theta, that's the adjacent over the hypotenuse. So you just write out adjacent over the hypotenuse. And that's the expression for cosine of theta. No inverse trig function needed. So I can say my x component of the electric field is equal to that KEQ over d over 2 squared plus y squared times this expression. And it simplifies a little bit. Square root of, well, maybe not that much. It simplifies this much. I can combine the denominator into this expression. So KEQ times still d over 2 divided by d over 2 squared plus y squared raised to the power of 3/2. Simple, it's a little bit simpler. So that times 2 will give you E net. So let me write that out. That should be 2 times KEQ times d over 2 divided by d over 2 squared plus y squared. I think I'm gonna run out of time. 3 over 2. So I'm definitely not gonna have enough time to do all three, or maybe let me see. Maybe if I don't waste too much time explaining, I can do all three. I do think I have enough time to do B definitely. So this is an integration exercise. You've had a homework question like this, so hopefully doing it again won't be too time consuming. So you have a rod like this, and we are looking for electric field at a point P, that's a distance B away. And when you are trying to find electric field by integration, the starting point is to express contribution to electric field due to some small representative element that's going to have charge dq. And you want to have parameters for expressing this representative element. Let's say I'm going to say my y is equal to 0 here. So this is at some position, and my positive y goes downward, and this is some at some location y. That's the expression I'm gonna use, and the thickness of this can be expressed with the dy, or length of that can be expressed with dy. Okay, so the contribution to electric field at this point, you use Coulomb's law, which says the electric field contribution, that's the d for infinitesimal, is Coulomb's constant times the amount of charge, the infinitesimal amount of charge, divided by distance squared. Let me rewrite this distance squared in terms of the parameters that are here. So I'm looking for this distance here. So there will be b plus y. So b plus y squared. And y is going to be positive. Good? Okay, so once I have that expression, and let me copy that down so that I can kind of put some spaces in it for things I'm going to be doing. So what you want to do is you want to think of a scheme to add it up. Add it up from basically where y is equal to 0 to where y is equal to L. So once you add up the contributions along the entire rod, that's going to give you the total electric field. And in order to do that, you have to express your expression for the infinitesimal charge dq in terms of your coordinate variables, in terms of your y and dy, or y and dy. And as you think of that, I hope this is an expression you can arrive at on your own somehow. Something like, so let's see, dq over q naught, so proportion of the total charge that dq is, that's going to be proportion of the total length L that dy is. Once you have that expression, then you can rewrite it into infinitesimal amount of charge is equal to move Q naught over L times dy. You can also think of this as this being the what we call linear charge density, lambda. So linear charge density times the length would give you the infinitesimal amount of charge. So once you have that, so let me replace that portion of the expression with that. dq is going to become Q naught over L times dy. Then now you have some idea to integrate this with respect to y from 0 to L, and that's going to be over the whole rod. So let's try doing this integral. Let me just scroll to right and do that integral. I'm going to factor out all the things that are constant, things that don't depend on y. That's going to be ke Q naught over L, and everything else depends on y. Y is equal to 0 to L. Am I going to need b plus y squared? This is one of those integrals that needs trig substitution. 7 minutes. Can I do trig substitution? It's been a while. Let me try doing it by hand. So I recognize I need a trig substitution because I don't have a linear factor of y above, so u substitution won't work. So the trig substitution, so I need to say y is equal to, I don't know, p. It's been too long since I've done trig substitution. I don't think I can do this. So this is allowed, so I am not cheating. You can use Wolfram alpha. Wolfram alpha will do simple integrals like this. So integrate. I'm too far out of practice to be able to do this under time limit in my head. Actually, can I do... sorry, I panicked too early. I think I can do u substitution. Sorry, not trig substitution. Because you can do this substitution. You can do u is equal to b plus y, and then go from there. I thought the squared was just on y, but it's not that. Squared is on the whole thing. So I can... I can panic too early. So with this u substitution, du is equal to dy. So you don't actually even have to change the numerator. You can just say, so let me actually change the line here. So you can say k q naught over L. And with the u substitution, the thing you have to remember to do is remember to change your limits. So as I change my variable to u, I have to plug in what y is and change the limits from b to L plus b, and dy will just become du over u squared. Now this is a simple algebraic, this is simple power formula, so I know the antiderivative of that. So ke q naught over L, u from b to L plus b. This is, so the form of this looks like u to the minus 2. So the antiderivative of that is u to the minus 1, or minus u to the minus 1. Sorry, I'm doing notation wrong. So the antiderivative of my integrand up there, that's minus u to the minus 1. And double check it for yourself by taking derivative of this in your head. This comes down, subtract 1, you get that. So with the antiderivative having been found, evaluated at the limit b to L plus b, and I can plug those in and get the expression. So plug in the upper limit first, minus 1 over L plus b, and then minus a plus lower limit 1 over b. And that looks about right to me. And I'm expecting, guess the way I define the direction of y, I'm expecting a negative number. And I got a positive answer. That's a little concerning. but it's probably fine. I know the direction of E, so I'll just say direction of it is upward, directly away from rod. And magnitude of E, I think that's actually correct. So I did verify this is going to be positive, so let me just plug in that positive expression. K Q naught over L times 1 minus 1 over L plus B plus 1 over B. So I think it came out to be positive because the way I set up my integral up here, with this expression, this is positive integrand. So when you integrate from regular integral with the upper limit being larger, this would be a positive number. So I think I was wrong in thinking it would come out to be negative. So it's all right, got that. Do I have enough time for the last one? 3 minutes. Probably if I try not explaining anything. So let me just try that. I'll just work on it silently. How much time do I have left? Okay. So direction, that's directly rightward. Um, well, doesn't sound right. Let me. There's a numerical factor I might be missing, but let me put in something within the time limit. Pi r squared. This will amount to some numerical factor that's either 2 or 1. Did I miss something? Pi, that's actually minus 1, so I was plugging the limit wrong. That was, so minus cosine of it's minus 1, and then minus that, so plus, and then cosine of 0 is plus 1. So yeah, they add up to be 2. Yeah, so I think I put in the correct answer there, unless I missed a factor somehow. Yeah, let's see. So if I did this right, so the second part will they won't grade correctly, but these should be using some auto grading system. So if I did them correctly, I should have gotten 50% of points. If I didn't, I will go into the solution and see, just so that we can for the purpose of 43%. Oh, I think that's actually right. There are 1, 2, 3, 4, 5, 6, 7 answer boxes, and of those, I can expect to have gotten credit for 3 of them. So 3 divided by 7, that's 43%. So yeah, I got all the 3 boxes correctly that I could have gotten credit for. So since I did this last one silently, the brief explanation of what I was doing. So in order to calculate the total electric field, I'm doing the same thing. I'm taking a representative element so that I can write an expression for the electric field contribution from that representative element and then integrate through. And I started working with only X component. By X, I mean, in this system. Because I realized that in integrating over this whole thing, any Y component will integrate, average out to 0. Or you can do the pairwise cancellation thing to see. So that's why I started with X component alone. And then I worked out the geometry to make sure that the way I decided to define theta, that I associated correctly whether it's sine or cosine of theta with the x. Here it worked out to be sine theta because the x component is the opposite side of the angle. So once I have that, then I set up the integral. I factor out all the things that are constant. It turned out to be a relatively simple integral involving just one trig function. So I did the antiderivative and I confused myself briefly in plugging in the limits, but before time ran out, I realized it'll be 2 and justified it later before time ran out. So so to attach work after the fact, the way you should do it is, in this view, you won't be able to attach work. So the easiest way to get to the screen where you can attach work is to refresh it. When you refresh it, you will get this button for adding work. So go to that and then add work. So let me just add all the work so that I finish this up properly. Yeah, from here, I think I can do it in, oops. That is really in the way. Can I? Okay, good. So there's work for A. Work for B. It's gonna copy in an overlapping way. And work for C. And again, for you, I recommend that you take some time to organize your work. There isn't any kind of time limit for attaching work. It does timestamp it, but I don't pay too much attention to it, as long as you're not changing your work after I've graded. So let me save work, and I can review that in this. So in this view, I can see the work but not change them, other than rotating it, rotating the image. And with this demo, I'm also hoping to demonstrate some of the things you should do while you are taking the assessment. And I'll also talk about some of the things that you will get from the system that you should ignore. Which I guess for the question type I'm attempting isn't affected, but some of the other question types, it might be affected. I'll explain why after the attempt. So let me get started with electrostatics freeform timed assessment. Again, I know what question I'm getting because I spent some time loading the dice for test student. So, and I'm gonna watch the time because I only have 20 minutes. Two infinite conducting plates arranged parallel to each other, separated by distance d, are connected to a battery. Okay, battery provides a voltage difference V. Okay, so let me do this. I'm gonna just paste this into the OneNote so that I can draw on top of this. Oops. Yeah, I think that's gonna be fine. Yeah. All right. Linked together. Oh, that could be good. Let's see if they are. Yeah. So describe briefly how following drawing should appear. Electric field lines should look something like this from the, does it describe upper plate at higher voltage? So plus V here, and I guess 0 volt here. Then electric field lines should look like this, and they should be equally spaced for uniform electric field from one plate to the other. So that's my electric field. And then equipotential surfaces, let me do it in different color with the dotted lines. They should look kind of horizontal. The main feature I'll be looking for is that they are perpendicular to the electric field. And the other, I guess, second main feature is that they should be equally spaced between each other. It's again tied to the fact that the electric field is uniform in this setup. So that's as best as I can draw freehand. So I'll be attaching this into attached work, but in the answer you should give a word description, like you are describing this to a blind classmate. So electric field vectors should be directed vertically from the plus V plate top to the lower 0 volt plate at bottom. The field lines should be evenly spaced throughout uniform electric field. The equipotential lines should be directed horizontally, perpendicular to the electric field lines wherever they cross, and the equipotential lines should also be evenly spaced, uniform electric field. Yeah, so that's the drawing. In our old midterm exam, I would have people actually just draw on the exam, but this is best I can get it to work in the online setting. So infinite plate. It can be proven that electric field between the two plates are uniform, has magnitude V naught over D. It can also be proven that the electric field outside the region between the two plates is exactly 0. Summarize the key points needed for the proof in the space below. You can also include, you can, don't have to. So key point. We start with the sense of the electric field directions. We drew for A above. Without explicitly saying that E field is 0 outside of the plate. So I might say for the drawing, let me say, including B, there could be electric field outside, you know. I think I don't have to necessarily say that electric field outside is 0. Outside of the plate, from the translational symmetry, translational, rotational around the axis perpendicular to the plate, and mirror, like flipping right and left, mirror symmetry of the setup. We know that E field can only be perpendicular to the plate, and the E field can only depend on the G coordinate, G axis being the axis perpendicular to the plate. If you move horizontally, that shouldn't change the E field that comes from the translational symmetry of the setup. Exploiting this symmetry, we can use a pillbox type Gaussian surface to show that electric field between the plates don't depend on the g coordinate either. Move the portion of a pillbox surface between the plates up or down. So I'm describing a Gaussian surface that kind of looks like this. So yes, just to show some perspective view. So this will enclose some charge. So that enclosed charge is what gives you the net flux, and you argued, that the electric field is uniform, so E dot A is constant and all that. So what you are then doing in this argument is imagining moving this surface up or down. And as you do, the flux doesn't change, which means electric field through this surface must not be changing. Either move the portion of the pillbox surface with the plates up or down. Net flux doesn't change, which also means the electric field doesn't change. Gaussian surface to show. And now how would you prove proving the outside fields must be zero is, I think that's a trick here, because if you do surface like this, then I think challenge is that with the field directions you could have non-zero field but zero flux. Zero flux that's mandated by the amount of charge you are enclosing. So I'll say following the example must be zero is trickier, but we can do it by doing the derivation of E field due to a single infinite plate. E is equal to sigma over 2 epsilon naught. That's a formula you can prove, and using superposition principle, because E field of infinite plate doesn't depend on G coordinate. The fields outside the plate exactly cancel. Yeah. So that's enough of a detail, and because I'm going to exploit the fact that question didn't ask for actual proof, it just said summarize the key points. So I did that, and by saying Gaussian surface, I'm implying that I'm using Gauss's law. I think that's enough. Maybe not the model answer, but it's one I'm giving within the time limit. All right. Calculate the pressure, force per area on the top plate due to the bottom plate through their electrostatic attraction. Oh, okay. So for CA, I guess what I have to be careful is that I don't include the field due to the top plate. So really what I have is the bottom plate will have negative charge on it. So it'll be producing electric field that looks like this on its own. Let me just finish with this one. It's going to be too many. And the expression for that electric field will be the amount of charge, which I don't know. But actually, sorry, I didn't fully complete B, I think. Uniform and has magnitude V over D. So let me finish that. The E field, the fact that the E field is V naught over D can be shown from the definition of voltage, which is that V delta V is equal to E times delta X. So here V naught minus 0 is equal to E times D. So E is equal to V naught over D. The effect. So this would be actually E average. fact the E is uniform between the fields, I mean, we can replace E average with E. Yeah, and I'll be making use of the fact while I'm doing part C. So here E would be sigma over 2 epsilon naught. And comparing that to the electric field that should be here, which is the sigma over epsilon naught, which is equal to V naught over D, I can re-express this in terms of quantities I have, which is half of that electric field, V naught over 2D. So that's the value of the electric field here. So for the top plate, which is here, the distance doesn't really end up mattering anymore. So if you imagine a little surface area element, the amount of force being pushed this way, the force would be the electric field times a small amount of charge dq. So you can express that the small amount of force on that is equal to electric field V naught over 2D times the small amount of charge dq. That's going to be the surface charge density times the area, dA. So it mentioned the pressure. If I have dF divided by dA, this will be the pressure. So all I have remaining is making sure that expression here is in terms of the things I have. I have V naught D, that's fine. Sigma is something that I don't have, but I can use this expression to express sigma in terms of things I know. So sigma is equal to epsilon naught V naught over D. So plugging that in, I have the amount of pressure is equal to V naught times V naught and D times D in the denominator. So it'll be epsilon naught times V naught squared over 2D squared. And just because I'm supposed to be trying to use the Coulomb constant more, I just have all the formulas memorized in terms of epsilon naught. But the substitution I'm using is the fact that Coulomb constant is equal to 1 over 4 pi epsilon naught. Or alternatively, epsilon naught is equal to 1 over 4 pi Coulomb constant. So I can replace that and say pressure is also equal to V naught squared over 4 pi times Coulomb constant times 2. So that 4 is actually 8 now. So that 4 is 8 pi k epsilon, ke times d squared. So this is these both are valid expressions for pressure. So yeah. Magnitude pressure is, so here, so I'm gonna get automatically graded. Somehow I didn't see that when I was looking at this question. So I'll get automatic grade, and I will talk about what that means, what it doesn't mean after I enter this. KE. Using this, one thing it helps you with is it helps you make sure that you don't use any variables that you shouldn't be using. So, all right, that's the magnitude of pressure, and this is the same answer you would get if you simply average the electric field inside, outside, and use the average value as the electric field on the plate. It just works that way. Let me not get into a rabbit hole that I don't have time for. If you release an electron in the middle, so like at d over 2. From rest, what is the speed of the electron, the moment before it strikes one of the two plates? Okay, so I think for what I'm going to use is conservation of energy. So this is actually physics 4A question. So just quick sketch. I'm releasing electron from here. It's going to go strike the positive plate and be here at the end. So let me call this a snapshot 1, call this snapshot 2. So if I have a sense energy is conserved from snapshots 1 to 2. So I'm going to say my total energy in snapshot 1 is equal to the total energy in snapshot 2. total energy in snapshot 1, just the potential energy. So here my voltage will be V naught over 2. Here my voltage will be V naught. So potential energy is minus E charge times V naught over 2 plus the kinetic energy is 0 at this snapshot because it's released from rest. In this snapshot, my potential energy is the charge times the voltage, and the difference will end up being E V naught over 2, plus the kinetic energy, 1/2 mv squared. I'm being asked for speed, right? Yeah. So it's a matter of just solving for this lowercase v for speed. So in the interest of time, I'm gonna do the algebra in my head. V is equal to the 1/2 cancel out. Square root of E V naught over M E. I think that's it. We'll look up the answer, see if I got it wrong later. So square root of E for the elementary charge times V naught divided by ME. And by the way, my open method understands implied multiplication, so if you didn't have this, it'll understand it fine. So I think that's it. So assuming I did everything correctly, when I get the score, I should get score of 50%. That's coming from these two that I hopefully answered correctly, and the rest. And these two are automatically given a score of 0, which is the part that I'm telling you should ignore, because all the manually scored parts, they just want you won't have any proper scores for that, because they are manually graded, and I'm not manually looking at this in real time or possibly ever. I'll talk about that in class. So I think I have 2 minutes. That might be enough time to add work. So yeah, let me add work. Now for adding work, this is what I recommend for you. For you, I recommend that you take some time to organize your work, or possibly even review it to see if you made any mistakes. So that is what I would recommend for you. For me, in the interest of time, I'm just gonna copy and paste this. I think this is enough for A and B. Yeah, the other figures, they were actually for C. So for C, I'll just include the whole thing. Let's see the entire set of figures here, and then I'll have to include this portion. And again, for you, I recommend that you organize so that you don't have to attach such difficult to decipher a jumble like I am right now. Did I mention test student is my worst student? He does things that I tell other people not to do. So with that, those are my work. Again, I recommend that you take some time to organize it. When we are doing the required one-on-one meeting, you will be able to see your own work. So why not, make it prettier? I'm gonna submit at the end. Now, when you do that, it won't actually end everything. It'll make it so that you can't edit these anymore. They are done. So either I got 50% or I missed something. But your work you can still change. In this screen, you still can. And I guess let me just save a work and continue. Now, after you get past that point, you can actually still, so I got those auto-graded portions correct. The other 50%, it's manually graded. So if you want to modify your work at this point, what you can do is you can refresh this screen and going through the add work button. Then you will get to a screen where you can still change the work if you feel like you need to change anything. If you go in through the review work in gradebook, that screen will not let you change anything. Not the answers, not the attached work. It just doesn't let you do any of that. Let you rotate the images for viewing convenience. So yeah, that's it. That's this one additional question that you don't have in the notes on the timed assessment page, and hopefully this is helpful to people looking at it.